solve problems we can't even touch today. But sometimes it feels, well, really abstract, right? Kind of disconnected from anything physical. So in this deep dive, we're going to try and ground that potential a bit, bring it down to earth.
Exactly. Yeah. We're looking at something really fundamental, Qubit encoding. You can think of it as the translation step, taking the math idea of a qubit and actually building it into something real. Whether that's a tiny supercooled circuit or like an atom trapped by lasers.
Right. And we've looked at some really fascinating sources that break down this challenge. And honestly, the different ways people are trying to solve it are pretty incredible. So our mission today, if you like, is twofold. First, understand why we need encoding. Why can't you just have a qubit? And second, explore some of the most promising ways folks are actually doing this.
And it all comes back to the qubit itself, doesn't it? This basic unit of quantum information, not like a classical bit, 0 or 1. The qubit can be in superposition, both 0 and 1 at the same time, sort of. That's where the power is, but it also makes it tricky when you want to, physically build one and use it.
Okay, let's jump right into that. Why do we need this encoding step? Why isn't it like having a transistor for a classical bit?
Well, like you said, the math is elegant, sure, but it's just math. It's abstract. To actually use quantum information, to compute with it, you need a physical thing, a substrate. It's a bit like having a great idea for an app. It's just an idea until you write the code and run it on hardware. Right? Qubit encoding is that step, taking the quantum concept and making it real in a physical system.
That makes total sense. So just pointing at something and saying, that's my qubit isn't enough. We need to be able to poke it, do things with it.
Definitely. First off, you absolutely have to be able to manipulate it, control its state. You need to perform those quantum gates we always hear about, like single qubit rotations, adjusting the chances of it being 0 or 1. And crucially, those multi-qubit gates, like the CNOT gate, that's how you get qubits entangled, working together for complex stuff.
Right, so control is key for computation. What else is non-negotiable?
Measurement. Definitely measurement. After you run your quantum algorithm, you need a reliable way to read out the answer. And that's when the superposition collapses, you get your definite 0 or 1. So the measurement has to be accurate, dependable.
And I guess thinking bigger picture, if we want powerful quantum computers, we need more than just one or two working alone.
Exactly. Interaction and scalability are huge. The encoding method you choose has to let qubits talk to each other effectively. And yeah, it needs to be scalable. You have to see a path, even if it's a long one, towards building systems with maybe millions of these things.
Okay, so physical representation, control, measurement, interaction, scalability. Wow. Yeah, that's a tall order. No wonder there are so many different ideas being tried out.
It's actually one of the most fascinating parts of the field, I think. The sheer variety of approaches.
Yeah.
And there's no single best way yet. Everything involves trade-offs. Maybe we should start with superconducting circuits. They seem pretty common.
Sounds good. Yeah, those are the ones you always see pictures of, right? Inside those big cold refrigerators.
That's the ones. Basically, tiny electrical circuits made on a chip, kind of like computer chips, but cooled way, way down, like fractions of a degree above absolute 0. Down there, some materials become superconducting zero electrical resistance. And the key parts are often these things called Josephson junctions. They're sort of special nonlinear circuit elements, crucial for making the qubit work, along with standard stuff like capacitors and inductors.
Okay, so super cold, superconducting circuits with these special junctions. How does that become a qubit then?
It usually comes down to the circuit's energy levels. They're quantized, meaning they can only have specific, discrete energy values. Think of it like a ladder. The qubit uses the two lowest rungs as its 0 and 1 states. And superposition is like being on both rungs at once. Now, how you define those rungs can vary. Like in charge qubits, it's about the number of Cooper pairs, these pairs of electrons in superconductors on a tiny section of the circuit. N pairs versus N plus 1 pairs, maybe.
Wow, okay, so a tiny difference in electron pairs is 0 or 1. What about flux qubits? Didn't you mention current?
Yep. Flux qubits use the direction of current flowing in a superconducting loop that includes Josephson junctions. So maybe clockwise current is 0, counterclockwise is 1, or vice versa. Then there are phase qubits too, using the quantum phase difference across a junction.
It's amazing how many ways there are even within one technology. You mentioned transbonds earlier. They seem to get a lot of attention.
They really do. Transbonds are a very successful type of superconducting qubit, basically a modified charge qubit. Their big advantage is they're designed to be much less sensitive to charge noise, random fluctuations in electrical charge nearby, which can mess up the quantum state. In a transmon, the 0 and 1 are the lowest energy levels of a kind of nonlinear oscillator made with the Josephson junction. This design just makes them inherently more stable against that noise.
Okay, that makes sense. Less noise sensitivity is good. How do you actually, control them and read them out?
Control is usually done with microwave pulses, very precisely timed and tuned pulses. Think of it like tuning a radio to a specific frequency. That pulse has just the right energy to flip the qubit state or put it in superposition. For measurement, the qubit is typically linked to something called a readout resonator. The qubit state slightly changes the resonator's frequency, or maybe the phase of a microwave signal going through it. By measuring that change in the resonator, you figure out the qubit state.
Okay, interesting. Microwaves for control, resonators for readout. Let's switch gears. Trapped ions. That always sounded like pure sci-fi to me, holding single atoms still.
It does sound like it, but it's very real. We use electric and magnetic fields, really carefully shaped, to trap individual atoms that have an electric charge, ions. These are held inside devices called Paul traps or Penning traps. And then crucially, we use lasers to cool them down until they're almost perfectly still, removes all the thermal jiggling.
And these trapped cold ions, how do they represent in 0 and 1?
It's all about their internal energy levels. The electrons inside the ion have specific energy states. Often they use two very stable, hyperfine ground states. These states are naturally well protected from stray magnetic fields, which is great for keeping the quantum information safe. This stability means trapped ions can have really long coherence times. They stay quantum for a long time. That's a big plus. Sometimes optical energy levels are used too.
So the atom's own internal energy configuration is the qubit state. How do you poke it? How do you measure it?
Lasers again. Lasers are the key tool here. You use one set of lasers to prepare the ion in a known state, like the 0 state. That's initialization. Then you use other lasers, tuned precisely to the energy gap between the 0 and 1 states, to drive it into superposition or flip it between states. That's control. And measurement often uses something called state-dependent fluorescence. You shine a laser that only interacts with, say, the 1 state. If the ion lights up, emits photons, you know it was a 1.
Wow.
If it stays dark, it was a 0.
That's incredibly neat. And how do they talk to each other, the multi-qubit gates?
Ah, that's clever. Since they're all trapped together, they share collective vibrations like they're connected by tiny invisible springs due to the electric forces. These vibrations are quantized too. They're called phonons. By using lasers to carefully manipulate these shared phonons, you can make two ions interact and get them entangled.
Okay, ions interacting via shared vibrations. Cool, let's move on to photons. Using light itself, that feels totally different again.
It really is a different approach. The qubit is literally a single particle of light, a photon. One big advantage is that photons don't interact much with their surroundings, so they're pretty resistant to noise and can travel long distances. That makes them really interesting for, say, quantum communication.
Okay, so how do you encode a 0 or 1 onto a single photon? Seems tricky.
Well, there are a few pretty neat ways. Polarization is maybe the most intuitive, like sunglasses, right? You can have horizontally polarized light B state 0, we call it Thoriate, and vertically polarized light B state 1. And any other angle of polarization, like diagonal, is a superposition of horizontal and vertical. Another way is path encoding. You send a single photon into an interferometer, basically a setup with beam splitters and mirrors. State 0 could be the photon taking the upper path. State 1 could be it taking the lower path. And the superposition, well, that's the weird part. Quantum mechanics is the photon takes both paths at the same time until you detect it.
Yeah, that both paths thing still gets me every time. Any other photonic tricks?
Sure. There's time bin encoding. Is the photon early or late? You define two time windows after some reference pulse. Arriving in the first window is 0 when, arriving in the second is 1. And you can also use the photon's frequency, or color. Different colors represent 0 and 1.
So many options. How do you control and measure these light-based qubits?
Controlling a single photon state, like its polarization or path, you can do with standard optical components, beam splitters, wave plates, phase shifters, stuff you find in any optics lab. Measurement just needs really good single photon detectors. Detect the photon, you measure the state based on which detector clicked or what polarization it had. The big challenge, though, is getting photons to interact strongly for those two qubit gates. They naturally just pass right through each other. So researchers need clever tricks, often involving measurement or special nonlinear materials, and these gates can sometimes be probabilistic, meaning they don't always work, which adds complexity.
Okay, that makes sense. Photons are good messengers, but maybe not so interactive. What about neutral atoms? Sounds like trapped ions, but
Exactly. No charge. So instead of electric fields, you use lasers to hold them, often using really tightly focused laser beams like optical tweezers that grab single atoms. Or you create a grid of light, an optical lattice where atoms sit in the little wells of light intensity.
That encoding, similar to ions, using internal energy levels.
Yep, very similar, usually using stable, hyperfine ground states within the atom for the 0 and 1. Good coherence. The neat trick with neutral atoms, though, for getting them to interact for gates, is often using Rydberg states. You excite an atom way up to a high energy level, a Rydberg state. In that state, the outer electron is really far out, making the atom physically huge and very sensitive to other nearby Rydberg atoms. It's like you temporarily puff them up so they bump into each other strongly, even from relatively far away. That allows for strong interactions needed for gates.
Ah, so you excite them to make them interact, control, and measurement. Also lasers, I'm guessing.
You got it. Lasers for cooling, trapping, state preparation, driving transitions between 0 and 1 for control. And measurement is often similar to looking for fluorescence, shining a laser that only one state scatters. Or
Ah,
sometimes you just check if the atom is still in its trap after trying to push one state out.
okay, next category. Quantum dots. The artificial atoms. Tiny semiconductor bits.
That's the idea. Nanoscale crystals of semiconductor material, so small that the electrons inside are really confined. This confinement makes their energy levels discrete, quantized, kind of like a real atom, hence the nickname.
And how do these artificial atoms hold a qubit?
A common way is using the electron spin. Every electron has a quantum property called spin, which can be up or down. So spin up is 1, spin down is 0. Simple as that, conceptually. Or you could use charge state, like is there an extra electron in the dot, state 1 or not, state 0. Or maybe which of two adjacent dots the electron is sitting in.
Spin or charge? How do you control that electron in its tiny box and see what state it's in?
Control is usually done with tiny electrodes nearby, applying voltages, gate voltages. These voltages can tweak the electron's energy levels or help manipulate its spin. Sometimes magnetic fields or microwave pulses are used too, especially for spin manipulation. Measurement often relies on spin-to-charge conversion. You set things up so that if the electron spin is up, maybe you can tunnel out of the dot easily, changing the charge nearby. If it's spin down, it can't. Then you use a very sensitive detector to spot that change in charge, which tells you the original spin state.
Clever. Okay, now for one that sounds really specific. NV centers in diamond, a defect in a diamond.
Yeah, nitrogen vacancy center. It's a specific flaw in the diamond's crystal structure. A nitrogen atom sits where a carbon should be, right next to a missing carbon atom, a vacancy. This specific spot creates a little quantum system with useful properties.
And that defect itself can be a qubit.
Exactly. The electron spin associated with that NV center works really well as a qubit. It's quite robust. And what's also cool is that the nuclear spins of the nitrogen atom itself, or nearby carbon-13 atoms in the diamond, can also act as qubits or quantum memories. So you can have a little quantum register right there.
What's the big appeal here? Why diamond defects?
One huge potential advantage is room temperature operation, or at least much closer to room temperature than superconducting circuits need. That simplifies things enormously. Control is done with microwave pulses, similar to magnetic resonance imaging, MRI, but for a single electron spin, it's called electron spin resonance. And lasers are used for initialization and readout. The NV center glows, fluoresces when you shine a green laser on it, but importantly, how brightly it glows depends on its spin state, so you measure the light intensity to read the qubit. Now, while room temp is possible, often for the very best performance, people still cool them down quite a bit, but maybe not to millikelvin temperatures.
Right, room temperature is a big carrot. Okay, last one, and maybe the most out there. Topological qubits, exotic particles, and braiding.
Definitely the most conceptually different and still largely theoretical, though experiments are making progress. The idea is based on using quasi-particles, not fundamental particles, but collective behaviors in certain materials that act like particles. Examples are Majorana, fermions, or anyons. These are predicted to show up in very specific systems, like materials in the fractional quantum Hall effect regime, or special nanowires combining superconductors and semiconductors.
Quasi-particles. Okay, and the encoding is totally different here.
Completely. The information isn't stored in a local property like spin or charge. It's stored non-locally in the system's topology. So specifically, it's encoded in how these quasi-particles are arranged and how you move them around each other, a process called braiding. The final quantum state depends on the history of which particles were braided around which others. It's like the information is stored in the knots you tie by moving them.
Whoa. So moving them is the computation.
Essentially, yes. Braiding operations correspond to quantum gates, and measurement involves probing the overall topological state, maybe using interferometry.
Oh.
The huge theoretical advantage, the reason people are so excited, is inherent robustness to local errors. Because
Yeah.
the information is spread out, encoded topologically, a little bit of local noise or disturbance shouldn't easily destroy the quantum state. It could be naturally fault-tolerant, or it's much easier to protect.
That sounds amazing. Like, solves the biggest problem. So why aren't these everywhere?
Well, the challenge is enormous, just unambiguously proving these quasi-particles exist in the lab and then controlling them precisely enough to do the braiding and read out reliably. It's incredibly difficult. It's cutting-edge physics research right now. Very exciting, but still early days experimentally.
Yeah, okay. That makes sense. Wow, what an incredible range of ideas, though, from circuits to atoms to light to defects to topology. It really shows how widely people are searching.
Absolutely. And to sort of evaluate all these different platforms, people often refer back to a set of benchmarks, the DiVincenzo criteria.
Ah, right. I've heard of those. They list the essential requirements, don't they?
Exactly. They lay out what you really need for a working quantum computer. First is scalability. Can you actually build a system with lots of well-behaved qubits? Then initialization. Can you reliably set all your qubits to a known starting state, like all zeros? Long coherence times are critical. The qubits need to stay quantum much longer than it takes to do a gate operation. You need a universal gate set, a basic toolkit of gates like single qubit rotations and a two-qubit gate like CNOT that lets you build any quantum algorithm. And finally, high-fidelity measurement, being able to accurately read out the final state of each qubit.
Okay, those 5 criteria really put the different approaches into perspective. You can see the trade-offs. Like maybe superconducting circuits look good for scalability because chip manufacturing is mature, but maybe coherence is tougher. Is that fair?
That's a very good way to look at it, yes. Superconducting circuits have shown great progress in scaling and control, but fighting noise for longer coherence is a constant battle. Trapped ions, on the other hand, often have fantastic coherence times and gate fidelities, really nailing those criteria. But scaling up to thousands or millions of ions in one trap while keeping control, that's a massive engineering hurdle.
Right.
Photons are great for coherence and communication, but those two-qubit gates are tricky. Neutral atoms are maybe a good balance. NV centers have that room temp potential, but maybe need better coherence still. And topological qubits, well, they promise amazing coherence and fault tolerance, but even demonstrating the basic building blocks reliably is still the main focus. That first criterion, just having scalable qubits, is the challenge right now.
It really drives home that picking how you encode your qubit isn't just some details. It affects everything about how you build the computer and what its strengths and weaknesses will be.
It's absolutely fundamental. It's the bridge between the quantum math and the physical reality of building the machine. And all this research across all these different platforms, pushing on coherence, on scaling, on control.
Right.
That's what's moving the whole field forward towards that ultimate goal, of large fault-tolerant machines that can actually solve those world-changing problems.
So wrapping this up, we've really journeyed through this amazing landscape of human ingenuity, all aimed at one core problem. How do you physically make a qubit? From freezing circuits to trapping single atoms, using light particles, even exploiting tiny flaws in diamonds. It's just fascinating.
And it's clear there's no single magic bullet yet.
Right.
Right? It's all about these complex trade-offs. Balancing stability control, scalability.
Yeah.
It really highlights how hard building a quantum computer actually is.
It definitely does. And it leaves you wondering, doesn't it? Thinking about all these methods superconducting, ions, photons, atoms, NV centers, maybe even those topological ones down the road. Which one seems most promising to you right now, and why? That's a question driving so much work in this field, something to ponder. Thanks for diving deep with us into how we actually bring qubits to life.